Thanks for coming. Thanks for those of you that are in my class for coming. It's really nice to have you. Yeah, so I'm going to be telling you about some of the instrumentation that we have been building at Cornell and in other places to study the early universe. And I will give you some, oh, hang on, there's some messages here. Okay. So one of the exciting things that I think about the universe is that we can study light from very, very far away. And um, use cutting edge instrumentation to figure out how the universe evolved, what the universe is made of, and maybe even how the universe will kind of continue in the future. So if you think about this from like the most basic standpoint, what we're doing is we're looking out in space and we're trying to use the things that we can see to understand our universe better. It helps if you have a telescope. It makes it a little bit easier. But beyond just looking out with telescopes that our eyes can see, if you have more powerful telescopes that do different things, you can actually see that the sky doesn't look just like some white dots, but that depending on the frequency of light that you're looking at, the sky has some very different characteristics and you can probe different structures. So the thing that you see in the middle is our galaxy. So if you're in a really dark place, right, you look out at the Milky Way and you can see that there's like this, very bright patch, and then you see the extragalactic stars all around. But when you look in other wavelengths, you can see that there are, bright structures outside of our galaxy. Our galaxy changes structure. Sometimes you can see like a very thin disk. Sometimes you can see like very diffuse gas. And when you're getting down to these low frequencies, so this is scanning from high frequency to low frequency now, we're looking at radio, you can see different structures there as well. And if our galaxy weren't so bright, you could see the cosmic microwave background really well. So just to give you some background, we talk about the light that we can see as the electromagnetic spectrum. So that just means that you have light and you have different frequencies or ranges of wavelengths. So that light that is coming towards you has a different energy level, and the waves of the light are either longer or shorter. And when you look at the spectrum with your eyes, obviously you see this narrow patch, but you can think of it as, going from higher to lower frequency or shorter to longer wavelengths. And then outside of those visible light frequencies, you have everywhere from gamma rays all the way down to long radio waves. And we are going to kind of capitalize on this to understand more about our universe than you could just with visible light. So now we're cosmologists and we're thinking, all right, what do we want to look at out there? And we also want to think about what technology we need to build to do it. And this has been happening for like centuries, right? Like folks are thinking, how can I build the first telescope? And then, how do you build a more powerful telescope? How do you build new technology to study things we haven't seen? This is something that we do. So when we think about what we want to look at, I mean, there's a lot of ways to go about this, right? Like there's serendipitous discovery, there's, theorists coming up with theories and us trying to disprove them. But I like to think about it as like what motivates us, like what do we want to know and also what we don't know. So I like to think about it as what is like really hard to measure because it's challenging, right? If it was easy, we would have already done it. But then also what is like on the edge where we actually could measure it? Because if you pick something that's just like so small a signal that you're never going to see it, it's not going to be so exciting. So kind of thinking about where we are and like where we can kind of take that next step to understand how our universe evolves, like what is the physics of our universe. So every single cosmologist has to be like, this is the history of the universe. So as we think, the universe started at this period of inflation. The universe expanded and cooled over time. Various things happened. We got to today. I'll tell you in a little bit more detail that we pretty much think that at the beginning of the universe, it expanded by a factor of 10 to the 78th in the first 10 to the minus 32 seconds after the Big Bang. It's postulated that this is caused by something called inflation, but as you can imagine, like this doesn't make a whole lot of intuitive sense, so there's something going on there that we don't understand. The other things that we might want to look at are like how do the elements form, how do they form first stars? This is a thing that we also don't understand very well. So we obviously know that we have stars today. We know that the stars have a lot of different elements in them, but we know that the universe probably started out just as helium and hydrogen. And how those first stars turned helium and hydrogen into the elements, we kind of understand that as well. But we really don't know what those first stars were like. So that's something that we kind of want to understand. We also kind of want to understand what happened after the universe started to grow a bit more and after we started to form stars and galaxies. So after the universe cooled enough, it was just made of neutral hydrogen mostly. There was a few other elements, but it was mostly neutral hydrogen. But when stars turn on, they start emitting very bright photons, and those photons can ionize all that neutral material, create bubbles, and eventually just turn it into the universe we have today. That's also far enough away that we don't really understand how that happened. And then the other things that we don't know are why the universe is now accelerating in its expansion again. So we have a couple of observations, including looking at supernova that explode and seeing that they look a little bit fainter than they should be if they were at the distance we think. So we know that we can extrapolate that that means that the universe is kind of speeding up in its expansion. So things that should be at one brightness are a little bit fainter. And that's actually kind of really well fit by data. So this plot up here is just showing you those measurements, and you can plot it versus a bunch of models of cosmology. And one of the models says that we have 70% dark energy in our universe right now, which is also kind of surprising. But what this is just showing you is that, as our universe expands, we have a lot of gravitational pull from all of the matter in our universe. So you might expect that it expands and it like slows down, and it did do that for a while. And then it started to speed up in its expansion. So that's just showing you the expansion speed. And that's another mystery that we would like to understand. So then we'll go on to the part where, how are we going to measure this? So there's a lot of different ways to do so. I'm just talking about one. But yeah, there's lots of astronomers and physicists out there trying to figure this out. I'll tell you a little bit about the way we do it. And I'll also tell you about something that's important for any of this to work, which is that when we're looking out in space, we're actually looking back in time. So we're not just seeing a snapshot of the universe today at every distance. As y'all probably know, the speed of light is incredibly fast, but it's not infinite, right? So it always takes light some amount of time to travel a distance. And that actually ends up being very lucky for us because instead of just seeing the universe today, we can actually see the universe at a variety of times in its past. The downside is you can't see the whole universe like as it evolves. So we only have one universe. That's a bit of a downside. But in general, you have even the sun, right? We always kind of, I feel like people talk about this when they're like, what's going to happen when the sun dies? But it's going to be 8 minutes before the light gets from the sun to us. That's always true, but we won't know it for 8 minutes. If you're talking about the nearby stars, so this is the closest star to us. It takes 4 years for light to get from Proxima Centauri to us, and that's 20 million miles away. Nearest galaxy, so Andromeda is our nearest neighbor, and it takes 2.5 million years to get from Andromeda to Earth. So we're seeing Andromeda as it was 2.5 million years ago. In cosmology time, that's still very, very nearby. But when you're looking at the faint radiation from the Big Bang, you're seeing the cosmic microwave background as it was basically 13 billion years ago. So that's the earliest light we can see, and it tells us what the universe was like at this incredibly, incredibly early time. But the same can be said for like the galaxies that are also quite far away, right? Like you have galaxies from here almost out to the cosmic microwave background, not quite. Actually, we don't know. That's one of the cool things. But you can see galaxies that are different ages, and that helps us understand the universe. So we need some technology to do this, and it's going to depend on kind of some of the things about the light that we're trying to see from those distant objects. And one of the things is that, yeah, we need something to detect light that's different from the one our eyes can see. And the reason for that is that there's this something called cosmological redshift. And this diagram is just showing you that at the Big Bang, the universe was like of some given size. It expanded, and the light that was in the universe expands along with it. So something that was very short wavelength when it was emitted stretches as the universe expands and is very long wavelength now. So we are like, all right, even if it was an optical emission from a bright star, it's now going to look millimeter to us. And so we need a different technology. The other thing is that we're on Earth. This is the atmospheric transmission of our atmosphere. So visible light gets through pretty well. That kind of makes sense for us. Um, but there's other wavelengths of light that are transmitted somewhat well, some not at all. So depending on what frequency of light you're looking for, you either need to be in one of those atmospheric windows or you need to go to space. The other thing is you need something that can detect those incredibly faint signals. So it happens that those signals that were emitted either, fractions of a second, billions of years, after the Big Bang, they are very faint by the time they get to us. And so we need something really cold so that the detector itself isn't actually like making noise that's bigger than the signal you're trying to actually see. And one of the cool things about this, so I don't know if y'all saw, but the Nobel Prize in Physics this year was for superconducting stuff. Like there have been a few for that. But in general, superconductors are pretty amazing materials and they allow us to do a lot of things that we wouldn't be able to do otherwise. So we actually build our detectors from superconducting materials. And we use cryogenics to cool our instruments. That's my grad student, Selena. Um, she said I could use this picture. So one of the cool things about superconducting sensors are that they have very low resistance, so you can, have electrical signals travel through them. And also because they're so cold, they're also not very noisy. And then there's some other properties that we'll talk about a little bit later. So that's a little bit about the technology. I'm going to go into detail about the detectors. So in general, if you want to make a measurement, you need something to gather the light, which is typically a telescope, and you need something to collect the photons. And so we usually call that a detector. And for the purposes of this talk, I'm going to pretend like the telescope part is really easy, but like my colleagues don't tell them. But you can buy a telescope. So you need some special telescopes, but the resolution has something to do with the size of the dish, right? So if you want to see really tiny things on the sky, you need a very large dish, so that complicates things. You need a really smooth reflective surface that's smaller than the wavelength, and you want it to be big also so that you can gather more light from faint objects. This is a telescope that we work on. That's JWST, which you probably know about. So maybe making telescopes isn't that easy, but it's not the hardest part for us. Okay, so the hardest part for us is detectors. And a detector is just basically something to absorb the photons and then something to record the signal. So for us, it's like our eyeball and our brain is like, okay, I saw that. Cool. So that's the most simple detector. In the past, we've used photographic plates to absorb the photons and then humans to actually look at those plates and record what objects are where. So that's another way to do it. But now we're really on to like highly technical detectors and then using computers to record the signals. So that makes sense. The other thing is, okay, so what do we need? We need a camera. Cameras, you can buy those too, but it really turns out like you cannot buy the kinds of cameras that we need to do this. Part of the reason I think is that they're just not super commercially viable. Like you don't really need a millimeter wavelength camera for that much. So there aren't ones that are just off the shelf. So you need this cold thing, and you need the sensor to be really large because you're looking for long wavelengths of light. This one's looking for nanometers, right? So we need some sort of specialized technology. And I'm going to tell you a little bit about two of the kinds of detectors that we use in these frequency ranges. So one of them is called the superconducting transition edge sensor. And that is basically just a detector that has something to absorb the photons, like I said, and then it has that superconducting material to be a very sensitive thermometer. And then, you have this like structure that, attaches it to the rest of the world, keeps it cold in the cryostat. And this is actually what it looks like in real life. So this absorber is this gold-plated web of silicon that's been etched away. It's incredibly delicate. And there's a very tiny piece of superconductor right there. And that superconductor basically responds when photons hit that web and get absorbed. So if you want some physics, this is the resistance of the sensor and the temperature is on the x-axis. And what this is showing is this is just what a superconductor looks like when you cool it down. So above the superconducting transition temperature, it's just a resistor. So it follows Ohm's law, top is flat. when it hits the superconducting transition, it actually drops very steeply. So the resistance drops incredibly fast, and then eventually it has zero resistance if it's like a perfect superconductor. This is great because what we've learned is that if you put a voltage across this sensor, it can heat it up, right? And then you can use that voltage to actually just like push it so that it like hangs out at this like very, very steep part of the transition. And so then if you get a photon that hits it and like warms it up a tiny bit, it changes the resistance a lot. So that makes it really sensitive. The other very cool thing is there's actually, the other very cool thing is that there's actually some feedback here. So when it warms it up, it actually changes the resistance, and then the current drops and it kind of cools it down. So it just hangs out in this transition, which is awesome. And it's really sensitive, right? So it's moving a lot in resistance, and we can measure out that change, and that gives us a very sensitive detector. There's another kind of detector that works in a different way, but also uses superconductors. Sorry, my computer is like balance. Okay, so remember how I was saying that when superconductors cool down, you get like a really easy flow of like electrons through the superconductor. So in addition to them flowing really well, for reasons that I maybe won't go into, but you can ask about after, the electrons kind of form pairs, and that allows them to like slide through the material lattice like very fast, and that's what makes a superconductor. Also, we don't fully understand what makes a superconductor. Like this is like a theory. There's like a few theories, and they like kind of work, but we don't really understand. But it works. And one of the cool things we can do with this superconductor is we can actually make an inductor. So if y'all remember from your physics classes, if you have an inductor and a capacitor, you make this resonant circuit at a certain frequency. And if you make that inductor out of a superconducting material, then it has those Cooper pairs. That's the electrons are called Cooper pairs. If a photon hits it, it can kind of break those Cooper pairs, and it turns out that changes the inductance. So anytime a photon hits that superconductor and changes the inductance a little bit by breaking Cooper pairs, it like scoots its resonance curve over a little bit. So you don't have to pay attention to these, but you can ask me about them later. But it just, that gives you the signal. So now you have this change in frequency as your signal. So there's a lot of ways to utilize these things, and they have low noise, right? Because they're very cold. So we're happy. The projects I work on, like one uses the transition-ed sensors, one uses the kids. They're called kids. I don't know why. The other thing that we need is a big array of these detectors because, like I said, we need incredibly sensitive instruments. So we need to build huge arrays. We fabricate them on these chips. We put like a bunch of them in a telescope. We've got good sensitivity. It's a little bit more complicated. So this is me in my lab. This is the mechanical design for our instrument, one of them. And this is me angle grinding things off that like didn't fit in the right place. So it's a little bit like, yeah, I tried. And there were some small things that needed to be changed. I actually think it's like good luck to angle grind things before you like install it. If you don't, it's like bad luck. But yeah, so this is just us putting this instrument together. Once you make that array, you have to put it in this huge cryostat. That's what keeps it cold. Like really, when you see the bulk of these instruments, it's like all of the stuff that's sticking off of them is just like to make it cold and to read out the electronics so that you can actually save the signal in your computer. And then eventually you have to lift the whole thing and all of its accoutrement into the telescope, and then you can start observing. So this is our instrument again. That's the telescope in the background. This is it being lifted. So you can see it's kind of like harrowing. That's like the scariest moment of my life. It's like hanging like 10, 20 meters in the air. So eventually that gets installed in the telescope. That's not the only telescope that we have. So this is like a telescope that you'll probably hear a lot about if you stay around Cornell. This is a telescope that is being built in the Atacama Desert in Chile. It's called the Fred Young's Millimeter Telescope, and it does very similar things. So it's the one that uses the kids. The one that I showed you before is the one that uses the transition-ed sensors. This is actually an artist rendering. It's like not done. They've basically made like this part of it so far. But in general, this thing will exist, and then we'll be able to build new cameras and put those cameras into this telescope and make more exciting measurements. All right. So does anyone have any questions about the instrumentation? Yeah, you can ask questions before I talk about the science again. Yeah, so they are supposed to just detect photons. It turns out that cosmic rays also like hit some of the like chip and like well you'll see like a spike if a cosmic ray hits your instrument. Um, for us, that's not a huge problem. Like we just like have a geometry where it doesn't have a lot of surface area for them to hit. But like some like if you've heard of the Planck satellite, so that was like a space mission that did similar stuff. They saw like tons of cosmic rays. It ended up being a huge problem for their data. So yeah, you can see other particles, but you don't really want to. Kind of, yeah. So cosmic rays look like very sharp and short spikes. And the signals that we see are much longer time scale. So if you like scanned over something that was the signal we're looking for, it looks like a very smooth thing. And a cosmic ray just looks like a spike. So what you do in practice is you like chop out that part of the data, but yeah, you'd rather not. Was there a question back there? No, go for it. Yeah, that is a fantastic question. The question, if you couldn't hear it, was when the photon hits the surface, does it not cause the photoelectric effect? And that's true that that would happen with an optical photon or a photon with higher energy, but it turns out one of the reasons we can't use like CCDs or CMOS for this kind of technology or for this kind of light is that it just has not enough energy to actually make the photoelectric effect happen. And so we're like stuck being like, okay, we have to think of another way to do this. So that's a great question. Yeah. Sorry, say again? Yeah, okay. Another very, very excellent question. Can you come do my job? So, one of the question was, does the stuff that reads out the detector also need to have low noise? And the answer is absolutely yes. And that's like a very hard problem as well. And some of the stuff that we work on in our research labs are to make the detectors work, but also a lot of folks are working on how to make a very low noise readout. And so it's like amplifiers that are very low noise. Sometimes it's like doing a lot of shielding so that like you don't get like RF pickup in the readout and all of that stuff. So yeah, the readout is incredibly important that that's also low noise. Yeah, great question. Any other questions about the instrument stuff? Okay. All right. So you can also interrupt me at any time. But now I'm just going to tell you kind of how these instruments actually tell us what we want to know. So again, remember we're like looking out. If you're looking at optical light, you'd point your telescope and you'd be like, okay, I see these things. I'm like hugely simplifying. But we have this radio telescope, and what it does is look at this microwave light. So instead of seeing, bright stars and galaxies and trying to understand what they look like, we just see this like blurry blob, and we just scan one piece of the sky over and over again, and we see this patchy thing. And the cool thing about this is that the patchy stuff actually has a lot of significance, in that if you do something like take the Fourier transform, which is basically say how much power is on what scale, like like is there really bright things, like are they very big? Are they at smaller scales? Like what is the power at what scale? That actually encodes tons of physics about how the universe evolved. So if you look at that Fourier transform of this map, you don't learn anything about individual parts of the sky, but you learn how the universe works on like a statistical scale. So there's a lot of stuff that happens like if you have like a peak at a certain point, like if the brightest peak is at a certain point, you can say, okay, that's where like all of the light was emitted at the surface of last scattering. So when the CMB was first emitted, like we see most of our light at this one scale. And so you're like, okay, we know that that happened. We know kind of that. You can see like when things happen, depending on, so the cosmic microwave background, that thing, um, it's basically a snapshot of like the density of the universe at that time. So there's places in the universe that are more dense and places that are less dense. And at that time, it's a plasma. So it's like electrons, photons, nuclei. They're all kind of like sloshing around. And gravity is making some of them like fall in to like the more dense parts because there's more dense and less dense parts. But because there's basically some friction there, you're getting like basically this like soup that's like oscillating. And so what you're seeing is actually that in the cosmic microwave background. The cool thing about that is that does tell you what that plasma soup is consistent of. So there's like dark matter, dark energy, regular matter. Dark energy We don't know so much about it. Um, but dark matter, we know that we think it's collisionless. So we think it can just like fly around very easily and not do things like create shocks. Like, so you know, when you have like a bunch of gas and you like shoot it into another bunch of gas, like you get shocks and stuff. So there's some basically frictional effect with normal matter, but with dark matter, we think it just kind of like slides through. So because of that, you can kind of tell how much dark matter versus how much normal matter is in there based on how these like oscillations of the early universe look like. So that's kind of cool. Um, the other thing is that you can kind of just see like what the total density is in dark matter and normal matter. And that's one of the things that actually made us think, oh, we think there might be dark energy out there because we knew how much total energy there should be in the universe for other reasons we can talk about. But we saw that there wasn't enough matter. And so we were like, there's something else. And it turns out that was dark energy. So there's a lot of things that you can learn. The other thing that you can learn from this is like, you might notice that that's like a full picture of the sky. So it's like a globe that's like a picture of the whole sky made by the Planck satellite, actually. It looks the same in every direction. Like that's not necessarily something that we think is obvious. And because it does, we think that the universe was compressed very, very much at the very early universe so that everything was in like what we call causal contact. But basically, then that expanded at this incredibly rapid rate and spread it out so far that like you wouldn't necessarily think it had like, you know, been in contact and been the same. So we're like, why is the universe the same in all directions? That's another mystery. Um, So yeah, we've learned what the universe is made of from looking at the cosmic microwave background. And this is just kind of like a graphic to show you what I just said, which is this is like this acoustic oscillation. So this is the Fourier transform of this basically. Um, this is a simulation of what it would look like. And this is like the black is the data points, right? So then this simulation is like what the power spectrum is what we call it. So what that power spectrum would look like if you had a universe that had basically, look, it says we have like, you know, a lot of atoms, a lot of cold dark matter, not very much dark energy. So that's like a universe that could exist, right? You're like, kind of makes sense. Dark energy, we don't know what it is. Why would there be a lot of it? But that looks nothing like the power spectrum of the cosmic microwave background that we see. So like immediately you would be like, this is a very bad fit to that data. Um, that's not what's going on. But if you have one that's, you know, a lot of cold dark matter, very few baryons, so what we're made of, uh, regular matter, and a little bit of dark energy, you're starting to get a little bit closer, like it looks a little bit more reasonable, but it's still very far off. And then, you know, you can get to something that's a little bit more like what we have. So this is, you know, 22%, 74% dark energy, 4% atoms. That's close to what we have. Um, but there's also a few other things that go into this that we also measure from the CMB, but that's like looking pretty good. And then with just like a couple of tweaks down here, you get basically the cosmic microwave background that we see today. So this is what it looks like for a model that is exactly like matched to the acoustic oscillations that we measure. And so that's like one way that we've discovered most of cosmology. So what we understand about cosmology, you know, we discovered by saying like, okay, cool, this fits to this very simple model and it kind of can encode what is dark energy, dark matter, regular matter. So that's kind of the big picture. But there's lots of questions still. And I will kind of try to show you a few of those. Okay, so remember how I mentioned that we think inflation happened? The circumstantial evidence for inflation is the fact that the universe looks the same in every direction. So what happened is that, you know, how I was saying that it's like very, very dense and then it expands. If you just think about the universe, like I'm looking out there and it took 13 point whatever billion years for that light to get to me, and I'm looking over there and it took 13.6 billion years for it to get to me. Like those couldn't talk by anything that we understand, like the speed of light or the speed of sound. You know, those things couldn't have actually been in contact with each other unless the universe was like much, much denser and then expanded very rapidly later on. Yeah. Yeah, I mean, we don't like that is totally, I think, unintuitive to us. Like, I think everyone thought that it would slow down. And there's even textbooks. I don't know if you read your cosmology textbook of like 1992, it'll be like, okay, mhm, we don't know. I mean, we don't know. Right. Yeah, and so if you like so if you look at kind of like the trajectory of what would be in contact with each other or out of contact with each other, so we like within or without like what we call the light horizon, that universe that expands just constantly without stopping, like doesn't have things at the edge of the universe in that direction ever having been in contact with each other. I should show you a plot afterwards. Yeah. Okay. I mean, so it's like it's more about like the speed that it happens, right? Because you need to like take something really small and then like blow it up really big and then slow it down so that it comes back in contact with each other. So, like, I mean, this is not trivial. Like, I look at a diagram that's like triangle, triangle, other triangle to know that. We can talk about it after. Like, none of this is like obvious, right? Like, you actually sometimes have to look at a plot or the math to be like, okay, that makes sense. Like, you don't have to just understand it from this. Um, so basically, we think this happened, and so we're like, how could we figure that out? And how could we find some actual evidence that that happened? And one of the things that we think happened is that if it expanded at that really, really rapid rate, it would actually stretch space-time as it was expanding and kind of create some oscillations in space-time. And that would actually cause an imprint on this cosmic microwave background because it would be stretching and squeezing like as it was being, as those density perturbations were hanging out. Um, and we know that from like the regular theory, every single this is very exaggerated, but if you look at those patterns, like they should be totally symmetrical based on all the physics we understand. So they should just look like roughly like the left-hand side. They shouldn't have any parity, like, my hands. But if that stretching and squeezing happened, it would actually cause like some asymmetric effects. They would actually have some like basically difference if you flip them. So what we're doing is we're like looking in the faintest parts of this to understand whether we see it just look completely symmetrical or whether there is this distortion. And that distortion is like 10 to the minus 7 times smaller than the thing you see there. So it's incredibly, incredibly small. So you're looking for an incredibly small signal on top of like a very large signal. But if you did see that, you could say like, oh, there are gravitational waves that happened in the early universe that caused this. We know gravitational waves exist because we've seen them with like LIGO and other things, but we haven't seen any that are made in the Big Bang. So that would be exciting. The other things that we can understand from just looking out at that structure is maybe what was happening with those first stars. So you can actually look at any structure. You can look at emission lines from galaxies. So that's like basically atoms and galaxies emitting some bright photons. You can measure those with your telescope, and we do the same thing. Like we just map out this fuzzy map of like any observable that we want to see, and then we try to understand what the structure is made of. And if those first stars and galaxies were emitting those photons, and say they were like from carbon, we would know that like, okay, we had to have had first stars make carbon by that time. So that can kind of start to pin down some of the stuff that we understand about first stars, which is kind of cool. The other thing is we don't really know where the gas came from and how much there is to make stars and galaxies. Basically, as we're getting closer to like the present day, we know that like the amount of stars that were forming was kind of like growing, and then it like peaked and then it kind of fell off. So we don't know why that happened, but we know that you need a lot of gas to make that happen because you need to make like clouds of gas collapse and make stars. So we want to understand how much gas is out there. Gas is cold. It's really hard to measure because it doesn't have a lot of emission because it's cold. So that's why we have to use these same technologies, right? Like it's a faint signal and it's in the millimeter. So it's just another one of those things that we have a hard time understanding with traditional tools because it's cold. But if we can understand how much gas there is, that helps us understand how stars form as we get closer and closer to today. And then the last thing is, back to dark energy. We know that universe is essentially a cosmic web. So that's just there's places that are very dense, and then there's places that are less dense, and there's places that are big voids. We know that because we've looked out at galaxies and counted them, and we have simulations of gravity, and they form that. Um, but if you look up into the sky and you like want to count all of those galaxies, like the gray is like a simulation of all the galaxies. It's really hard. Like even with a really powerful telescope, you'd measure like the red dots. That's what we're trying to say. But if you have a different telescope like the kind we build, you can just kind of scan over and see everything as like this fuzzy low resolution blob. But then you can do the same thing that you do with the cosmic microwave background, which is you take the Fourier transform and you see some statistical things that tell you like how much carbon was at this time, how much carbon monoxide gas was in this time. Like so you can start to use that to probe the structure. That's very cool because one of the things that we want to do is we want to probe the structure as it evolves over time because we will see a different structure depending on how much dark energy there is. So we can use that as a way to see if dark energy is evolving or it's just like staying the same. If we can actually like see how much the structure grows. And that's just because, right, like that dark energy is pulling the structure farther apart. So it's going to be less dense. Or say it's like, not growing, like not staying the same, it's growing, it's shrinking, whatever. You can see that when you see that structure and how it affects that structure, like how dense or how less dense the structure is. So that's kind of the last thing that we want to do. So I guess what I'm trying to get across is that like we have this technology and it actually allows us to probe things in the universe like over the whole range of cosmic time, which is kind of exciting. And it allows us to probe things that are incredibly faint, incredibly far away. And that's kind of where I'm talking about at the beginning, like, we're kind of like pushing the edge of like, what can we do? Like these detectors are almost not sensitive enough to do this, but like they're getting better and better and we're building better and better ones so that we can actually do this. Like the dark energy part, that requires like 100,000 of the detectors that I showed you. Like right now we're making like 2,000. So that's kind of what we're talking about. We're like really pushing those edges and also trying to come up with new technologies that are more compact that could really make a telescope that had 100,000 detectors in this wavelength range. So yeah. Also, it's really fun. So that's where I'm going to stop. I'm going to say it's really fun. You get to be with all your friends and build stuff, and you get to go to telescopes, and you really get to push the edge of what we know about our universe, and you get to kind of use your ideas to come up with like new technologies, like new ways that we could read out detectors, like new kinds of detectors, because we're thinking about a different way that you can do this. And yeah, these are my students here at Cornell at Kip Peak, and all of these projects are hugely collaborative. Like the Fred Young Similometer telescope I showed you, that probably has like 100 or 200 people working on it. My main project has like 30 people working on it. So you're always working with students and postdocs and faculty like across the world. And I have a lot of undergrads working in my lab here. It's really awesome. You should talk to me if you want to do that. I'm like using this as my advertisement. But yeah, but also like a lot of credit for all of this super hard work goes to all of these people that are doing this. And that's like everyone in our group, I think. So I'll stop there. Thanks.
All right. Thank you so much, Professor Crites. Now is the time for any questions, but just if you do have a question, could you raise your hand so I can run the mic over to you so that people on the Zoom can see it? And anyone on the Zoom, if you also have any questions, you can put them in the chat. So, does anyone have any questions? No. Oh, yes. Okay. 1 second.
Um, you said we can measure dark matters by using these telescopes. I wonder, is it directly or from a statistical model?
Yeah. So the question was, can you measure dark matter directly with these telescopes? And the answer is no. No one has really measured dark matter directly yet. There's so much astronomy that has shown us that dark matter exists. So if you look at how fast stars are orbiting around the center of our own galaxy, like they would be orbiting way slower if there was no dark matter. If you look at how clusters orbit each other, like we have all of this evidence, including stuff in the cosmic microwave background, showing we definitely have dark matter, but we have like never ever been able to observe it directly. So that's a huge open question in physics, and people are trying to think of ways to do it because it doesn't interact. It's so hard. One of the things people do is like basically make these incredibly clean tanks of like materials that have really huge nuclei, so that like hopefully a dark matter particle will run into the nucleus, because we know they don't interact with the electrons like regular matter, and then it would like kind of knock it, and we could measure that. But there's so many signals that look like that. It's just like an incredibly difficult problem, so no one's solved that yet.
I see. I think people make comparisons to like dark matters and the ether that they thought lights travel.
Yeah, yeah, no, totally.
Is there like some experiment like the Michelson experiment that could be conducted
Sorry,
for
say
that?
again.
Is there like experiments like how Michelson did for ether that could be used for dark matter?
Yeah, so the question was like, okay, so I don't know if y'all know the history, but so people thought if light is a wave and can travel through the universe, it must be traveling in something. So they tried to measure that by using an interferometer, basically. So an interferometer basically takes light in one way, it goes through a beam splitter and splits it off into two arms, it recombines it, and then measures it at a detector. And so if anything is changing in that arm, then it will cause like an interference pattern. Instead of seeing the signal you put in, you see like basically pattern that looks slightly different depending on changing length of the arms. So they use that to prove there was no ether. But we do use like similar interferometers to show that there are gravitational waves. So the LIGO interferometer is an interferometer that showed that if you have a colliding black hole, they cause these gravitational waves. They'll change the length of the arms, and you'll be able to see that that happens. But like, I mean, that's an interesting question. Like, I think that like the thing you're thinking about sounds really cool. Like, it sounds very futuristic, but it sounds like, okay, well, what if you put more matter like here? And like, I think that, and you had this big interferometer, could you see it? Like, I don't think that that is like totally out of the realm of possibility. It sounds like a lot to think about, but I think it's a really cool idea.
Thank you.
Do we have any other questions? Yes. Look, come around.
Hi, thanks, Professor Crites. So how do you deal with like, like bad microwave ovens and stuff like that? How do you like get rid of interference?
Yeah, good question. So the question was, how do you get rid of interference? So y'all probably know, probably from my class, there's Faraday cages, right? So like we put a Faraday cage around all the electronics. We usually kind of the same way that we look at like kind of get rid of cosmic rays. It's like a similar thing where like the signal looks very different from our actual signal. So some of it we just like filter out. But we have filters on like the electronics to filter out the frequencies we don't want in there. There's lots of different ways. I mean, there was famously this like discovery of like these things called fast radio bursts that actually like some of them were actually literally a microwave like in the telescope cabin. So it's like not totally crazy. But yeah, there's a lot of different ways to do it. I mean, we have problems with this all the time though. I mean, one of the good things about being at like remote sites is that like you have less interference from humans, but it's like Starlink satellites like are now like super prevalent. There's tons of interference from those. Some of it's RF that like gets picked up by stuff like this. Some of it's like visual that gets picked up by optical telescopes. But yeah, I mean, there's tons of interference and it's not like a trivial problem.
Anybody else? Yes.
Following up on that question, how do you deal with the interference from other things in space, not on the Earth?
Yeah, great question. So the question was, how do you deal with interference from other things in space? And it really depends on what you're trying to do. So I'll just give an example of like, how I was saying we're trying to find these galaxies that have carbon that are really far away. And I was also like, oh, we can also measure gas that's nearby. It turns out like the things that are far away, like they emit photons, and then the photons from the nearby sources also get in your same telescope, and you're like trying to see how they look. That's a huge problem for us. So basically, like two of our science goals overlap each other. Like one of them is like really far away and hard to do, but like the one nearby is easier. But then we have to get rid of the signal from those nearby galaxies. And so we have a couple of ideas for that. One of them is just to use a galaxy catalog of all nearby galaxies and just take the map and like cut out all the pixels that have those. Like you have to understand how you're doing that so you're not creating like other problems. There's also like there was a famous like scandal in like 2014 in the cosmic microwave background world, because how I was saying that those like gravitational waves from inflation could like twist the CMB a little bit and cause this like asymmetrical pattern. Our own galaxy also looks exactly like that. So when you saw that very first picture that had the galaxy in the middle, and then, there was less stuff up here, but not none. Basically, you have to be pretty sure that you're subtracting away all of the emission from our galaxy because it looks like our signal. And people published a paper and like got super famous for like 3 months until everyone was like, just kidding, that wasn't actually like that signal. And they like thought they were gonna get a Nobel Prize. Like they were like on the streets being like, we're brilliant. And then like they were like, no, actually that was our own galaxy. Whoops. So yeah, I mean it's a huge problem. I don't think that it's hard. Like all of this is hard, right? So it's normal, but a lot of the things that we have to think about are we have to build an instrument that has like 7 different frequencies instead of 1 because we know that the galaxy looks different as a function of frequency than the cosmic microwave background does, so we can subtract it. Like there's lots of different ways that we can think about solving these problems, but like none of them are easy. Yeah.
Anyone else have any other questions? Yes. Ooh, sorry, it might take a second for me to get to you.
To keep the streak of talking about noise going, so if you do get a lot of noise, when you're processing that, is that mostly through like digital means, or is there still a human element present in it? And how is like AI factor into that now that it's here?
Yeah, so the question was like, do you digitally filter or humans? And the answer for us is kind of like both. So it kind of depends what we're trying to do, but a lot of the times these things are confusing enough that like we look at them, like we look at each of them. We were just talking about this in group meeting today. So we look at every single map and are like, yeah, that one has some crazy stuff going on. Like it's not very scientific, but we're like, yeah, that's messed up. But as we get to these bigger and bigger instruments, like the ones that have 100,000 detectors, like no one's going to look at every single map from every single detector. And so we are going to have to find a robust way. And like, yeah, machine learning and all of that is one of the ways that we're thinking about how we can do that, because the signals are really complex. Like it's not like, oh, like this thing has one spike here, like there's something different going on and it's hard to understand that. So either you have to cut a ton of data or you have to figure out like a smarter way to figure out what's good and what's bad. But yeah, it's like, still right now it's like definitely some of both. Yeah. And especially for the instruments in their early stages when they're like not working so great, you're like, well, let's like try to figure out the one detector that's working super great, like it is kind of like a very messy process. Yeah.
Anyone else? Yes. Here you are.
Sorry. So, how do you figure out like basically like from the question before, what emission is like from the galaxy and what isn't?
Yes. So in the specific question of like what emissions from the galaxy versus what's from the cosmic microwave background, it turns out that we know that the emission from our galaxy mostly comes from something called synchrotron radiation, and then it also comes from just dust and like the molecules in dust like emitting. And we can actually measure those and we know what their spectrum looks like. So we know that if you look at the spectrum with respect to frequency, so if you're like looking at a plot and frequency is increasing, the dust kind of like increases really steeply and the synchrotron like decreases really steeply. And the cosmic microwave background just looks very flat. So it just looks like flat as a function of frequency. So that's what I was mentioning earlier, is if you have like say 7 frequencies and you can measure the sky as a function of frequency, then you can like subtract out those other slopes and then the underlying thing will be just your CMB left over. That's like in the best case scenario, right? Like it might end up being harder than that, but that's one of the ways. Yeah, so there's kind of like a bunch of different things, but a lot of the instrument design has like that taken into account because that is so hard. So like I was saying, the first instruments, people just had one frequency. They're like, let's just measure this as well as we can at one frequency. And then it was like, oh wait, that's not going to work. We need to like have a bunch of frequencies. And then there's something else like how I was saying that you get that like distorted signal from the early universe expansion. You also get that from like something called gravitational lensing, which is that when light comes towards us, it's like distorted by all of the galaxies and stars like between us and the cosmic microwave background. So now you have a distorted signal when I just said like the only place you can get a distorted signal is like this really cool phenomenon. It turns out there's another way you can get it and you also have to remove that. And so there's like all sorts of things in that case, like you need a telescope that can measure that really well so that you can subtract it. So it's like there's a lot of stuff.
Any other questions? All right. If not, thank you all so much for coming again. If we could get one last round of applause for Professor Crites. Just as a quick reminder, if you guys are interested in attending the remaining lectures we have this semester, they can be found on our website under events. And as always, Fuertes Observatory will be open from 8 p.m. to midnight tonight. So thank you all so much for coming.
Not get into it because basically that like you have like a lattice of like positive ions in a material, right? So like in general, like a material is like, you know, a bunch of ions plus the electron, especially if the electron kind of crazy. Yeah. And when you are like the electrons are like they attract that and it felt like it's one electron bounce like the positive ions get but then that actually makes it work. So another electron actually get closer to it than it normally would. Yeah. Just